Fiberglass is the common name for glass-reinforced plastic or alternatively glass fiber-reinforced plastic. Fiberglass is also known as GFK, for German, Glasfaserverstärkter Kunststoff. Fiberglass is a fiber-reinforced polymer made of plastic reinforced by glass fibers, commonly woven into a mat. The plastic may be a thermosetting plastic, most often epoxy, polyester or vinylester, or a thermoplastic. Fiberglass is a strong lightweight material and is used for many products. Although it's not as strong and stiff as carbon fiber, it is less brittle, and its raw materials are much cheaper. Its bulk strength and weight are also better than many metals, and it can be more readily molded into complex shapes. Applications of fiberglass include aircraft, boats, automobiles, bathtubs and enclosures, hot tubs, septic tanks, water tanks, roofing, pipes, cladding, casts, surfboards, and external door skins. Fiber. Unlike glass fibers used for insulation, for the final structure to be strong, the fiber's surfaces must be almost entirely free of defects, as this permits the fibers to reach gigapascal tensile strengths. If a bulk piece of glass were defect-free, it would be equally as strong as glass fibers. However, it is generally impractical to produce bulk material in a defect-free state outside of laboratory conditions. Production. The process of manufacturing fiberglass is called pultrusion. The manufacturing process for glass fibers suitable for reinforcement uses large furnaces to gradually melt the silica sand, limestone, kaolin clay, fluorspar, culminate, dolomite and other minerals to liquid form. It is then extruded through bushings, which are bundles of very small orifices. These filaments are then sized with a chemical solution. The individual filaments are now bundled in large numbers to provide a roving. The diameter of the filaments, and the number of filaments in the roving, determine its weight, typically expressed in one of two measurement systems, yield, or yards per pound. Examples of standard yields are 225 yield, 450 yield, 675 yield. Tex, or grams per km. Examples of standard tex are 750 tex, 1100 tex, 2200 tex. These rovings are then either used directly in a composite application such as pultrusion, filament winding, gun roving, or in an intermediary step, to manufacture fabrics such as chopped strand mat, woven fabrics, knit fabrics or unidirectional fabrics. Sizing, a coating or primer is applied to the roving to help protect the glass filaments for processing and manipulation. Ensure proper bonding to the resin matrix, thus allowing the transfer of shear loads from the glass fibers to the thermoset plastic. Without this bonding, the fibers can slip in the matrix, causing localized failure. Properties. An individual structural glass fiber is both stiff and strong in tension and compression, that is, along its axis. Although it might be assumed that the fiber is weak in compression, it is actually only the long aspect ratio of the fiber which makes it seem so. That is, because a typical fiber is long and narrow, it buckles easily. On the other hand, the glass fiber is weak and shear, that is, across its axis. Therefore, if a collection of fibers can be arranged permanently in a preferred direction within a material, and if they can be prevented from buckling in compression, the material will be preferentially strong in that direction. Furthermore, by laying multiple layers of fiber on top of one another, with each layer oriented in various preferred directions, the material's overall stiffness and strength can be efficiently controlled. In fiberglass, it is the plastic matrix which permanently constrains the structural glass fibers to directions chosen by the designer. With chopped strand mat, this directionality is essentially an entire two-dimensional plane. With woven fabrics or unidirectional layers, directionality of stiffness and strength can be more precisely controlled within the plane. A fiberglass component is typically of a thin shell construction, sometimes filled on the inside with structural foam, as in the case of surfboards. The component may be of nearly arbitrary shape, limited only by the complexity and tolerances of the mold used for manufacturing the shell. Applications: fiberglass is an immensely versatile material due to its light weight, inherent strength, weather-resistant finish and variety of surface textures. The development of fiber-reinforced plastic for commercial use was extensively researched in the 1930s. It was of particular interest to the aviation industry. A means of mass production of glass strands was accidentally discovered in 1932 when a researcher at Owens, Illinois directed a jet of compressed air at a stream of molten glass and produced fibers. After Owens merged with a Corning company in 1935, Owens Corning adapted the method to produce its patented fiberglass. A suitable resin for combining the fiberglass with the plastic was developed in 1936 by DuPont. The first ancestor of modern polyester resins is cyanamides of 1942. Peroxide curing systems were used by then. During World War II, fiberglass was developed as a replacement for the molded plywood used in aircraft radomes. Its first main civilian application was for the building of boats and sports car bodies, where it gained acceptance in the 1950s. Its use has broadened to the automotive and sport equipment sectors. In some aircraft production, fiberglass is now yielding to carbon fiber, which weighs less and is stronger by volume and weight. Advanced manufacturing techniques such as prepregs and fiber rovings extend fiberglass's applications and the tensile strength possible with fiber-reinforced plastics. Fiberglass is also used in the telecommunications industry for shrouding antennas, due to its RF permeability and low signal attenuation properties. It may also be used to conceal other equipment where no signal permeability is required, such as equipment cabinets and steel support structures, due to the ease with which it can be molded and painted to blend with existing structures and surfaces. Other uses include sheet-form electrical insulators and structural components commonly found in power industry products. Because of fiberglass's lightweight and durability, it is often used in protective equipment such as helmets. Many sports use fiberglass protective gear, such as goaltenders and catchers' masks. Storage tanks. Storage tanks can be made of fiberglass with capacities up to about 300 tons. Smaller tanks can be made with chopped strand mat cast over a thermoplastic in a tank which acts as a preform during construction. Much more reliable tanks are made using woven mat or filament wound fiber, with the fiber orientation at right angles to the hoop stress imposed in the side wall by the contents. Such tanks tend to be used for chemical storage because the plastic liner is resistant to a wide range of corrosive chemicals. Fiberglass is also used for septic tanks. House building. Glass-reinforced plastics are also used to produce house building components such as roofing laminate, door surrounds, over-door canopies, window canopies and dormers, chimneys, coping systems, and heads with keystones and sills. The material's reduced weight and easier handling, compared to wood or metal, allows faster installation. Mass-produced fiberglass brick effect panels can be used in the construction of composite housing, and can include insulation to reduce heat loss. Piping, GRP and GRE pipe can be used in a variety of above and below ground systems, including those for fire water, cooling water, drinking water, wastewater sewage, natural gas, construction methods, fiberglass and layup operation. A release agent, usually in either wax or liquid form, is applied to the chosen mold to allow finished product to be cleanly removed from the mold. Resin typically a two-part polyester, vinyl or epoxy is mixed with its hardener and applied to the surface. Sheets of fiberglass matting are laid into the mold, then more resin mixture is added using a brush or roller. The material must conform to the mold, and air must not be trapped between the fiberglass and the mold. Additional resin is applied and possibly additional sheets of fiberglass. Hand pressure, vacuum or rollers are used to be sure the resin saturates and fully wets all layers, and that any air pockets are removed. The work must be done quickly, before the resin starts to cure, unless high-temperature resins are used which will not cure until the part is warmed in an oven. In some cases, the work is covered with plastic sheets and vacuum is drawn on the work to remove air bubbles and press the fiberglass to the shape of the mold. Fiberglass spray layup operation. The fiberglass spray layup process is similar to the hand layup process, but differs in the application of the fiber and resin to the mold. Spray-up is an open molding composites fabrication process where resin and reinforcements are sprayed onto a mold. The resin and glass may be applied separately or simultaneously chopped in a combined stream from a chopper gun. Workers roll out the spray-up to compact the laminate. Wood, foam or other core material may then be added, and a secondary spray-up layer embeds the core between the laminates. The part is then cured, cooled and removed from the reusable mold. Poult operation. Poult is a manufacturing method used to make strong, lightweight composite materials. In Poult, material is pulled through forming machinery using either a hand-over-hand method or a continuous roller method. In fiberglass Poult, fibers are pulled from spools through a device that coats them with a resin. They are then typically heat-treated and cut to length. Fiberglass produced this way can be made in a variety of shapes and cross-sections, such as W or S cross-sections. Chopped strand mat or CSM is a form of reinforcement used in fiberglass. It consists of glass fibers laid randomly across each other and held together by a binder. It is typically processed using the hand layup technique, where sheets of material are placed in a mold and brushed with resin. Because the binder dissolves in resin, the material easily conforms to different shapes when wetted out. After the resin cures, the hardened product can be taken from the mold and finished. Using chopped strand mat gives a fiberglass with isotropic in plane material properties. Warping. One notable feature of fiberglass is that the resins used are subject to contraction during the curing process. For polyester this contraction is often 5 or 6%. For epoxy, about 2%. Because the fibers don't contract, this differential can create changes in the shape of the part during curing. Distortions can appear hours, days or weeks after the resin has set. While this distortion can be minimized by symmetric use of the fibers in the design, a certain amount of internal stress is created. And if they become too great, cracks form. Health problems. In June 2011, the National Toxicology Program removed from its report on carcinogens all biosoluble glass wool used in home and building insulation and for non-insulation products. However, NTP considers fibrous glass dust to be reasonably anticipated, as a human carcinogen. Similarly, California's Office of Environmental Health Hazard Assessment published a November 2011 modification to its Proposition 65 listing to include only glass wool fibers. The actions of US NTP and California's OEHHA mean that a cancer warning label for biosoluble fiberglass home and building insulation is no longer required under federal or California law. All fiberglass wools commonly used for thermal and acoustical insulation were reclassified by the International Agency for Research on Cancer in October 2001 as not classifiable as to carcinogenicity to humans. The European Union and Germany classify synthetic vitreous fibers as possibly or probably carcinogenic, but fibers can be exempt from this classification if they pass specific tests. Evidence for these classifications is primarily from studies on experimental animals and mechanisms of carcinogenesis. The glass wool epidemiology studies have been reviewed by a panel of international experts convened by the International Agency for Research on Cancer. These experts concluded, epidemiologic studies published during the 15 years since the previous IARC monograph's review of these fibers in 1988 provide no evidence of increased risks of lung cancer or mesothelioma from occupational exposures during the manufacture of these materials, and inadequate evidence overall of any cancer risk. Similar reviews of the epidemiology studies have been conducted by the Agency for Toxic Substances and Disease Registry, the National Toxicology Program, the National Academy of Sciences and Harvard's Medical and Public Health Schools, which reached the same conclusion as IARC that there is no evidence of increased risk from occupational exposure to glass wool fibers. Fiberglass will irritate the eyes, skin, and the respiratory system. Potential symptoms include irritation of eyes, skin, nose, throat, dyspnea, sore throat, hoarseness and cough. Scientific evidence demonstrates that fiberglass is safe to manufacture, install and use when recommended work practices are followed to reduce temporary mechanical irritation. Fiberglass is resistant to mold, but growth can occur if fiberglass becomes wet and contaminated with organic material. Fiberglass insulation that has become wet should be inspected for evidence of residual moisture and contamination. Contaminated fiberglass insulation should be promptly removed. While the resins are cured, styrene vapors are released. These are irritating to mucous membranes and respiratory tract. Therefore, the Hazardous Substances Ordinance in Germany dictates a maximum occupational exposure limit of 86 mg/m³. In certain concentrations may even occur a potentially explosive mixture. Further manufacture of GFRP components creates fine dusts and chips containing glass filaments, as well as tacky dust, in quantities substantial enough to affect people's health and the functionality of machines and equipment. The installation of effective extraction and filtration equipment is required to ensure safety and efficiency. Examples of fiberglass use: surfboards, tent poles, gliders, kit cars, sports cars, microcars, carts, body shells, boats, kayaks, flat roofs, lorries, K-21 infantry fighting vehicle, minesweeper hulls, pods, domes and architectural features where a lightweight is necessary, high-end bicycles, auto body parts, and entire auto bodies, antenna covers and structures, such as radomes, UHF broadcasting antennas, and pipes used in hex beam antennas for amateur radio communications, FRP tanks and vessels. FRP is used extensively to manufacture chemical equipment and tanks and vessels. BS 4994 is a British standard related to this application. Most commercial vlimobiles, most printed circuit boards consist of alternating layers of copper and fiberglass FR4, large commercial wind turbine blades, RF coils used in MRI scanners, subsea installation protection covers, reinforcement of asphalt pavement, as a fabric or mesh interlayer between lifts, helmets and other protective gear used in various sports, orthopedic casts. Fiberglass grating is used for walkways on ships and oil rigs, and in factories. Fiber-reinforced composite columns, see also, glass fiber-reinforced concrete, bulk molding compound, sheet molding compound. References